Hello, everyone. Hopefully you can hear and see me. Um, but my name is Saleem. Oh, and also today we're going to be giving a talk on gas chromatography and also a bit of mass spec. You may have been expecting liquid chromatography, so I'm so sorry, but it'll be gas chromatography this week. So I'll just get going if that's okay. So my name is Saleem, and I'm a out of program registrar in the first year of my PhD, funded by the MRC. And today I'll be giving you a talk about gas chromatography and mass spectrometry because I've needed to optimize a method as part of my PhD using GCMS, especially to measure amino acids. So I'll just talk to you a bit about that and also GCMS relevant to the chemical pathology curriculum. So maybe before I begin talking about how I started to optimize a GCMS method, I'll give you a 30-second background about my PhD, which is essentially optimizing glucagon, which I'm sure you all know about, but for the treatment of obesity, fatty liver disease, and type 2 diabetes, because glucagon's ability, when it binds to the hepatocyte, to lower liver fat is now being translated to treat several metabolic diseases and it's now being combined with GLP-1. But the problem is, when you give glucagon chronically, it can cause sarcopenia, as shown by this graph. So when you activate the glucagon receptor, you upregulate the urea cycle. And that will draw in alanine coming from the catabolism of these branched-chain amino acids, valine, isoleucine, and leucine, liberating the ammonia group. And then that alanine is a scavenger amino acid, bringing it into the liver, eventually disposing of that ammonia. In the same way, like glutamine, glutamine does a similar option or a similar thing. So I'm really hoping with my PhD to find a way of being on this side of the seesaw of using glucagon to really lower liver fat, which is beneficial for type 2 diabetes, obesity, and fatty liver disease, but avoiding amino acid catabolism. So therefore, it's really crucial I can measure amino acids as part of my PhD. And there are kits available. So this is a kit by Merck, and you can measure you can measure total amino acids using a fluorometric kit, but that will give you the value of all the amino acids collectively. I want to measure each individual amino acid. I want to know how much alanine there is, valine, leucine, threonine, methionine. So I decided to optimize a way of, with one sample, being able to measure all these amino acids. And when I started this journey, I guess, I found this graph quite helpful. You have molecular weight here on the y-axis and then the volatility of these compounds here on the x-axis. But you can see that compounds with a low molecular weight that are highly volatile, like alcohol and ketones, are great for GCMS. But things like peptides, lipids are better. Proteomics, lipidomics is better to be measured using LCMS. And then you have amino acids here, which kind of fall in the middle. But the reason I went with GCMS is because the machine that we use, the Agilent system, is robust, whereas the LCMS machine where I work is less robust. So any assay that uses a mass spectrometer as the final detection method will have 3 steps to it. You'll have sample preparation, chromatographic separation, and then detection using the mass spec. And I just talk you through this. The first step, sample preparation, that can be as simple as dilution, or it can be as complex as solid phase extraction or immunoextraction. Then the second step is obtaining chromatographic separation. This is using gas or liquid chromatography, which is what's typically used. And then finally, you have mass spectrometry to do that. And my method's not perfect, but it's good enough. And I'll just talk you through sample preparation, then gas chromatography, and then I'll talk you through mass spectrometry. So this is an Eppendorf. Sorry, in the background is my hand, and these are my creases on my hand. Sorry about that. But this is an Eppendorf containing plasma from a mouse. So this is 7 microliters, which is a very small amount of mouse plasma. But from that 7 microliter sample, I can extract almost all amino acids and up to 45 metabolites like urea and ornithine. And as a clinical chemist, it's not unusual to work with small samples. And a good example, drawing an analogy, is in dried blood spot testing, which I'm sure you all know about, whereby you get a heel prick from a baby, put that blood onto a filter paper, and then from those dried blood spots, literally spots of blood, you can screen for various inherited metabolic diseases in newborns. And the way to extract that blood from that filter paper is to use solvents. And in the same way, I also use solvents to extract metabolites, amino acids from my plasma sample. And I use methanol, water, and chloroform. This is LCMS grade methanol and water to extract those amino acids. And I'll just mention one thing which is also relevant to clinical chemistry is the use of an internal standard. And I use an internal standard, silicate inositol, and you add that to every single sample. But if you add it to the water, that gets into all of the samples. And the reason adding an internal standard is so important in clinical chemistry, but also in academia, is that it allows you to internally standardize your run. Because you know the concentration of the internal standard, and that allows you to account for variations in things like sample preparation, the instrument response, or even the injection volume. And another real great benefit of using an internal standard of a known concentration is that it can estimate the relative concentration of an unknown by comparing it to the known concentration of an internal standard. And you just do a ratio of the two. So methanol, water, and chloroform with the internal standard are then mixed with my plasma sample from mice. And then after that, I subject those samples to sonication. In here, this is a chilled sonification bath. And then they undergo high-speed centrifugation. Now, I don't know if you can see this, but hopefully you can. You can see that the speed, this RPM is 15,000. That's really fast. In a clinical chemistry lab, you might spin things at 4,000 RPM. But this 15,000 RPM is also clinically relevant. At Imperial, the way we manage lipemic samples is that we subject them to high-speed centrifugation at 15,000 RPM, where you remove that top lipid layer from the spun sample and you then measure the infranatant. But remember, if you're measuring things in that way, you can't measure hormones and drugs because you're removing that lipid layer. And when I subject my samples to high-speed centrifugation, you see the same pattern. You see a separation of phases, as shown by this Eppendorf, where you have this top layer. This is the aqueous phase, and this contains the amino acids and metabolites. And this phase beneath it, this non-polar organic solvent phase, contains lipids and lipid species that have been partitioned away because of chloroform. So what I do is I aliquot some of this aqueous phase containing the amino acids, put it into vials, and then essentially dry them down because the GCMS does not like water. So you really have to dry down these samples. We also add methanol as well to further dry them down. And then this is what it looks like. You can maybe just see here this white powder sitting at the bottom of the inlet of that liner within the tube there. Now, once you've got your dried sample, the next step is derivatization. And why do you need to derivatize? Well, for two reasons. Number one, to make the compounds volatile, but also to make them thermally stable. And I cannot stress the importance of that enough. And it will become apparent shortly. But the compounds we use to make, well, the derivatives we use to make the compounds volatile and thermally stable are methoxyamine and BSTFA, which stand for bis-trimethylfluoroacetamide, or just BSTFA. And here it is. This is methoxyamine diluted in some pyridine, and then BSTFA is here. You then add these agents to your samples, you then cap them, and then they're ready to run. Now, you've prepared your samples. That takes about 6 hours. And then once you've prepared your samples, you then begin loading them on the GCMS. And that is probably one difference between GCMS and LCMS. From my understanding and my learning and my experience, is that the preparation of samples with GCMS is generally longer than that of LCMS. So I find this diagram quite helpful for seeing an overview of gas chromatography mass spectrometry. So here is where you inject the sample into this high temperature inlet. This here is a GC column, and the GC column is within an oven, a very high temperature oven. And then the sample leaves the column and then it enters the mass spec, where you have an ionization method to basically add a charge to the molecules, and it's then detected via the mass spectrometer. And this is the output you get. So you'll get a very big graph, which is the total ion chromatogram with various peaks. And if you hover above these peaks, you'll essentially get a signature of that compound. And you'll have fragments of, of different ions from, let's say, alanine. And by knowing those fragments and their mass over charge ratio, you can very specifically identify certain compounds. So we'll just talk about gas chromatography and then mass spec. I don't know if we need to know this, but there are two ways that I know of injecting samples into the GC. One is a split injection, where some of the sample is discarded. The other way is splitless, where some of the sample is not discarded. And this is how the sample enters the GC. This is just a cartoon here, but let me talk you through it because I think this is very important. So the sample goes into the GC, and this is a high temperature inlet liner. That's really key because that high temperature inlet liner vaporizes your sample, as seen by these small bubbles here. So your sample expands and it vaporizes. And here's the inlet liner here. So your sample is introduced here. This is the high temperature inlet liner. So your sample becomes vaporized, essentially into gas, and it's then transferred into the column of the GC, being pushed through by your mobile phase, which is the gas in gas chromatography. And the common gases that are used are helium, which is what I use, hydrogen, and also nitrogen. The advantage, I think, of hydrogen over the other two is that it allows faster analysis, but I use helium. So once though that liquid sample is vaporized from that inlet liner, it makes its way down into the column. And this is the GC column. So the column that I use is a capillary column, and it's lined with silica. So therefore, silica is the stationary phase of the column. And this is just in an animation, but that vaporized sample comes down, comes through the column, and those molecules in that gas phase then adsorb, adsorb to the stationary phase. Now the GC column is within an oven, and that oven begins at a temperature of 60 degrees. But as you ramp up the temperature all the way up to 370 degrees, as I do in my method, the metabolites then begin to separate, and they separate according to their boiling point. And it's metabolites that are more volatile with a lower boiling point, they elute sooner than metabolites with a high boiling that are less volatile with a higher boiling point. So this blue molecule, perhaps this is alanine because it has a retention time of about 6.6. This may elute at a temperature of say 70 degrees. But something like tryptophan, that might elute at a temperature of say 300 degrees Celsius because those amino acids have different boiling points. And by knowing that chemistry, you can use that to your advantage in this method. So this really highlights why it's so important to select derivatizing agents that allow your molecules to be thermally stable. Because if I subjected alanine, just regular alanine, into this oven, it would degrade. But by adding, what the derivatization agents do is that they add, you need to know this, but I'll just say it to you anyway, it adds a TMS group. And that TMS group has a methyl group, and that methyl group allows these molecules to withstand high temperature. So that's why it's important to select the right derivatizing agents for this method. And then it goes to the mass spec. And for for anything to be measured on the mass spec, it needs to be in the gas phase and needs to carry a charge. So far, tick, the molecules that I've used are in the gas phase, but how do they become charged? Well, they become charged via ionization methods. And I just listed some here. Usually in LCMS, not GCMS, but in LCMS, you might use electric spray ionization or atmospheric pressure chemical ionization. In GCMS, the most widely used ionization method is electron ionization. This is a hard ionization method because in this method, what happens is that these molecules travel through a really high energy beam of electrons. And as they pass through that high energy beam of electrons, these molecules become ionized, they become charged, they form cations. And because you're using 70 electric volts, which is very high, you also fragment the molecule into a series of smaller positively charged ions. So this EI basically just blasts the molecule with electrons, giving it a charge and fragmenting it, to put it simply. And then the next phase is the mass analyzer. And I use single quadrupole, but here are some other examples, and I'll just explain this. So once the molecule has undergone ionization, you can make lots of different molecules. For example, this molecule. So this molecule has a mass of 400 and a charge of +1. So it has a mass to charge ratio of 400. Molecule 2 has a mass of 1000 but a charge of +2. So it has a mass charge ratio of 500. So clearly this molecule will hit the detector sooner than this molecule. And so this mass analyzer will separate the molecules, the quadrupoles, and then those molecules that need to hit a detector, there needs to be a readout, and that's done using the mass spectrometer. So this molecule will hit the detector, so this will separate it out, and then this molecule will hit the detector before this molecule. I should also say that this is a bit fictitious because usually in GCMS, the charge is often 1. But this is really just for illustration purposes to hopefully show you how you ionize the molecules. The mass analyzer separates out those molecules of different mass charge ratios, and they're then detected by the mass spectrometer. And this is what you get if your experiment works, which for me it didn't to begin with. But this shows the total ion chromatogram, where you have the x-axis here is time, retention time, and the x-axis is ion counts. And you can so the method that I use, we have programmed that method to only detect these metabolites. So for example, if we zoom here on 6.6, I know this peak here is alanine. So we're now focused on alanine. And if you zoom in, this is the TMS derivative of alanine. It needs to be TMS so it can withstand that high temperature in the GC oven. And you can see 2 peaks. So the first peak, and you can see, I don't know if you can see that, but the retention time is about 6.66. And you can see this light purple peak is mice treated with placebo who you'd expect to have normal alanine. And this darker peak here is mice treated with glucagon who you'd expect to have low alanine. And that's what happens, which you can see. And I know this peak is alanine because if you look at this is the mass spectrum. This is the mass spectrum of the different mass charge ratios of this peak. This 1116 ion is specific for alanine, and if you see this ion, you can quantify that peak because you can say this is alanine because of the retention time and the ion. And I know this because, I mean, there are so many libraries that confirm this. You know, people have made libraries from GCMS, LCMS, and they've highlighted that some things are alluded to at a certain retention time with a specific ion 1116. Here are some more. This is glutamic acid. Control mice, treated mice. You can see the treated mice have less glutamic acid, and the 246 is the quantifier ion for glutamic acid, so we can quantify this peak. Here is leucine, control mice, treated mice, and you can see the treated mice have less leucine than the controls. And again, this is the quantifier ion for leucine, 158. This is isoleucine here. As well. Here's methionine, which has the ion of 176 into it, and this is lysine, which has 174. So this really highlights the beauty of mass spec. It's so specific, it's so selective in being able to identify your molecules of interest. If you did an amino assay, there's so much other rubbish in plasma. That can cross-react with a detection antibody, etc. It can displace your molecule from that site, the hydrogen hook effect. But with mass spec, it's just so much more selective. So it gives me real great pleasure to show you this graph. And this graph just shows concentration on the y-axis and all of the different amino acids we've been able to measure from a small amount of mouse plasma. The dark bars are glucagon, the lighter bars are vehicle, and you can see that the amino acids are lower in the glucagon-treated mice. So, from such a small sample, you can measure all of these amino acids plus up to 45 other metabolites I've not included here, which is really powerful. And the other benefit is that you can measure things at very low concentration, sensitive, with using such a small volume. So that is almost me done. But this is the most important slide of the whole talk. None of this would have been possible without Zaki, who is a scientist that I work with at the MRC LMS. And Zaki has supported me, helped me run these assays. We've done long hours coming in at 8 o'clock, leaving late at night in the lab to be able to optimize this GCM assay for no benefit of his own other than my own benefit. So it really shows that how medics and scientists can work closely together to get a great outcome. And that's my contact details if you have any questions. But thank you very much. And I think that's me done.